On a cold April night in 1941, a lone Wellington bomber waited on the dark field at RAF Mildenhall. Its canvas-covered frame glowed faintly under the Suffolk moon, looking more like a fragile experiment than a machine built for war. Yet inside, squadron leader James Ward and his 5-man crew moved with quiet confidence. They had flown together for 8 months, 23 missions behind them. Another dangerous trip ahead. The plan was routine, or so the briefing claimed. Take off, cross the North Sea, reach Bremen, drop incendiaries and high explosives, and return home before sunrise. Intelligence officers even hinted the German flak defenses were thinner tonight. It should have been straightforward. What no one said aloud was the argument spreading through Bomber Command about the Wellington itself. Unlike American or German bombers with shiny metal skins, the Wellington looked outdated. Irish linen stretched tight over a strange lattice framework, a geodetic design created by engineer Barnes Wallis. Many pilots trusted metal. Few trusted fabric. Some crews even asked to transfer to Hamptons or Whitley's simply because they felt safer. Ward wasn't one of the doubters. He'd seen the geodetic frame hold together after a February raid when flak tore a hole in the port wing big enough for a man to crawl through. And the aircraft still flew home straight and steady. He believed in Wallis' unorthodox engineering. But belief didn't stop the questions whispered in every briefing room. Could a fabric-covered bomber survive modern cannon fire? At 2,100 hours, the Pegasus engines growled to life, drowning out any last moments of doubt. Minutes later, the Wellington lifted off the runway and disappeared into the black sky. Once they crossed the English coast, navigation lights went dark. From that moment on, they were alone, sharing the night with German fighters hunting exactly this kind of prey. Wind tunnels and mathematics said the geodetic structure could take heavy damage. But the skies over Germany were not a laboratory. Tonight those theories would face their harshest test. The first warning came at 22:45, 30 miles from Bremen. "Skipper, we've got company, 7 o'clock high," the rear gunner reported, trying to sound calm. A Messerschmitt Bf-110 night fighter swept in, guided by its new Liechtenstein radar. Ward pushed the Wellington into a shallow dive, but the German fighter held every advantage: speed, altitude, and an experienced pilot. At 600 yards, the fighter opened fire. 4 machine guns and 2 20mm cannons spat metal across the night, the shells exploding on impact. The Wellington's fabric skin offered no protection. Bullets punched through like it was paper. The navigator saw starlight shining through fresh holes only seconds old. But the German pilot made one mistake. He fired too early. Ward threw the bomber into a tight climbing turn, bleeding speed to force the fighter to overshoot. It worked. The Bf-110 flashed past and broke away. The relief lasted only 40 seconds. A second night fighter dove from above. This pilot was patient. At 300 yards he opened fire. Accurate, deadly. Exploding shells hit the geodetic frame, sending shards of metal spinning through the interior. Rounds cut electrical lines, ripped into the wings, and punctured fuel tanks. Then the ground fire began. Bremen's 88mm guns filled the sky with bursting shells. Shockwaves hammered the Wellington, each blast adding new holes to the already shredded skin. Instruments began failing one by one, airspeed jumping wildly, compass fluid leaking, oil pressure flickering. Yet something remarkable was happening. The Wellington kept flying. The controls felt steady. No violent shaking. No sudden roll. Even with dozens of holes and cut cables, the aircraft behaved almost normally. In the wireless operator's compartment, bullets passed clean through the fuselage, entering one side and exiting the other, slipping between the curved metal ribs without hitting anything vital. One round nicked his desk, spraying wood splinters across his logbook. And still the Wellington held together, pressing on toward the heart of Germany. Even as the bomber rattled from every hit, the crew kept noticing the same impossible fact: the Wellington was still holding its course. 17 bullet holes surrounded the wireless operator alone, fabric flapping wildly in the slipstream. Another round had punched clean through a parachute pack on the wall. It looked like the inside of a machine already doomed, but the aircraft refused to fall. The first Bf-110 pilot, convinced he had already destroyed the bomber, swooped in for a second attack. He fired a short, concentrated burst, around 120 rounds from his machine guns and cannons. Through his canopy, he watched strips of fabric fly away, pieces of framework break off, and debris fall into the dark. He believed no aircraft built of linen and light metal could survive such punishment. Confident he had delivered the final blow, he turned away to hunt new targets. But Ward's Wellington never spiraled, never dropped, never smoked. Warning lights glowed across the instrument panel, yet the controls stayed responsive. What kept the aircraft alive wasn't luck, it was the strange geodetic skeleton Barnes-Wallis had designed. Every time a structural member snapped, its load shifted instantly into dozens of neighboring members. The lattice absorbed damage the way a spiderweb absorbs the loss of individual strands. It bent, but didn't break. The second German pilot, a veteran with 11 bomber kills, immediately sensed something was wrong. Every bomber he had ever shot down showed classic signs before dying: losing altitude, leaking flame, rolling uncontrollably. This Wellington did none of it. It simply kept flying toward Bremen like a wounded animal refusing to stop. He made a third attack run, focusing carefully on the engines and cockpit. The burst tore another 40-plus holes through the Wellington, 3 passing so close to Ward that fragments clipped his jacket. A cannon shell struck the main spar behind his seat with a sharp crack that echoed through the entire frame. But again, the bomber stayed solid. With his ammunition almost gone and fuel low, the German pilot finally gave up. He marked the bomber as probably destroyed in his combat report, too embarrassed to admit it had escaped him. Inside Berlin's intelligence offices, the Luftwaffe's technical analysts had been studying the Wellington since 1938. Their reports accurately described its size, crew, armament, and range. But they all repeated one critical misunderstanding. They dismissed the geodetic structure as outdated and weak. A widely circulated 1939 document described the Wellington's fabric and basket weave frame as unsuitable for modern war, claiming the British used it only because of industrial shortages. From that mistaken belief, German night fighter doctrine was built. Training manuals at the Schleißheim Night Fighter School taught pilots that a Wellington would break apart after a short, concentrated burst. They were instructed not to waste time confirming the kill. If you hit a Wellington properly, it simply stopped flying. And this doctrine worked perfectly on other bombers. Hamptons, Whitleys, and similar aircraft with more conventional construction all failed quickly under heavy fire. But Wellingtons were different. They kept returning to England with damage that should have been fatal. Pilots reported seeing them hit, torn open, fabric streaming, and then vanishing into cloud instead of falling. Intelligence officers explained away these contradictions as poor visibility or pilot inexperience. No one in Berlin considered that the British design might be far stronger than it looked. Barnes-Wallis had never meant to start a revolution. His ideas grew from his work on the R-100 airship, an 800-foot giant that taught him a single lesson: spreading load across many members made a structure far stronger than concentrating it in a few. The R-100's geodetic pattern, spiraling metal ribs forming endless triangles, handled stress by sharing it across the entire frame. Wallis adapted that concept into an aircraft without longerons, without traditional load paths. Instead, thousands of small alloy members crisscrossed in opposite spirals from nose to tail. Where they met, they formed rigid joints that transferred stress in every direction. Damage to one piece didn't threaten the whole frame. It simply shifted to the surrounding structure. Inside a Wellington, roughly 1,700 individual alloy members created this woven skeleton, light enough to keep the aircraft efficient, strong enough to keep it alive when every rule of aircraft design said it should already be falling from the sky. And tonight, high over Germany, that strange lattice was the only reason Ward and his crew were still alive. Every structural member in the Wellington linked into a network of at least 6 others, creating so much built-in redundancy that losing any single piece reduced total strength by less than 0.1%. What made the system truly remarkable was how it behaved under uneven loads, the exact situation created by cannon fire. When several members on one side were blown apart, their loads didn't pile onto the nearest surviving pieces. Instead, the stress flowed through the entire lattice, finding new routes through nodes and intersecting ribs, sometimes carrying forces all the way across to the opposite side of the fuselage. The structure healed around damage automatically, without any action from the crew. When Wallis first proposed this, many Vickers engineers dismissed it as needless complexity. Building more than 1,700 precision-machined pieces and fitting them together like a three-dimensional puzzle seemed slower and more expensive than traditional longerons and formers. But early tests revealed unexpected advantages. The geodetic frame weighed less than a conventional structure of equal strength, giving the Wellington better range and payload. It was also easier to repair. Because each member carried only a fraction of the overall load, individual pieces could be replaced without disturbing the surrounding structure, something impossible in long-run-based aircraft. Ward brought the damaged Wellington back across the North Sea at reduced speed. With fabric torn in dozens of places, the bomber felt different in the air. More drag, more vibration, but nothing dangerous. They had already dropped their bombs over Bremen and escaped the fighters. With the compass shot out, the navigator used the stars to guide them home until the dark outline of the Suffolk coast finally appeared. Ward landed at 2:30 on April 6th, touching down as gently as on any previous mission. The ground crew approaching the aircraft in the darkness saw nothing unusual, until Flight Sergeant Thomas Fricks swept his torch across the fuselage. The beam froze on damage so extensive it barely resembled an aircraft at all. The Wellington looked like a metal basket stretched over with shredded cloth. Fricks began the standard damage count procedure. White chalk marks circled every hole, numbered and logged. At first, the crew worked normally. But as the count passed 50, then 100, then 150, work slowed and the men simply stared. They had repaired bombers before. They had patched torn fabric and replaced broken ribs. But nothing they had ever seen had survived this level of punishment and remained flyable. The final tally, checked 3 times, was 203 separate penetrations. 87 machine gun rounds had passed clean through without striking anything vital. 41 rounds hit structural members, breaking 11 completely and damaging 30. And 19 cannon shells caused heavy localized destruction. 56 holes came from flak fragments peppering the rear fuselage. The most astonishing detail was not the quantity but the luck of distribution. Control cables to the tail had survived untouched despite dozens of holes around them. 3 fuel tank punctures were sealed by their rubber bladders. Electrical lines were damaged, which explained the failing instruments, but backups had kept the control surfaces working. Even the turret hydraulics, though cut, had not caused mechanical failure. Fricks walked the length of the aircraft twice, trying to reconcile what he saw with every principle of conventional aircraft design. By normal standards, this bomber should have broken apart over Germany. Enough members had been hit to doom an ordinary fuselage. And yet it still sat on its wheels, its geometry intact and its main structure sound. Then Fricks made a decision only someone familiar with geodetic construction would dare. Instead of classifying the bomber as Category 3, requiring weeks at a repair depot, he marked it as Category 2, reparable on station within 48 hours. Bomber Command needed every airframe it could keep in the air, and this one, astonishingly, was still fundamentally strong. 14 men gathered to repair it: riggers, electricians, fitters, and armorers. They had barely 4 hours before daylight. The work began with structural checks. Each damaged member was inspected, tested for hidden cracks, and then either reinforced or replaced. Where a member had snapped completely, the fix was simple: cut out the broken section and splice in a new piece with fish plates on both sides. Because geodetic members were individually accessible, a fitter could repair one in minutes, something impossible on a traditional bomber where major sections had to be dismantled. Fabric repairs followed. Small holes were patched with doped fabric that shrank tight as it dried. Larger shredded areas were replaced entirely with fresh panels from stores. The electrical crew worked wire by wire, checking continuity and rerouting cables away from sharp metal edges. The wireless operator station, nearly ruined by gunfire, required installing a complete replacement harness of 16 wires threaded through the lattice back to the radio equipment. And still the men worked on, racing the coming dawn, determined that this torn, punctured, unbelievable aircraft would fly again the next night. An electrician worked nearly an hour and a half on that single wiring harness, crouched in the cramped fuselage with only a torch for light, checking every splice before moving on. By 0500 hours, most of the structural work was finished. 11 geodetic members had been replaced outright, another 32 strengthened with fishplate reinforcements, and the framework load-tested using sandbags on the wings and fuselage. Deflection readings matched those of an undamaged airframe, confirming the structure was again carrying loads as intended. Fabric teams patched 197 of the 203 punctures. The remaining 6, all in non-critical tail sections, were left open because they posed no threat and added negligible drag. And so, at 2,000 hours on April 6th, barely 17 hours after Ward had landed the shredded bomber, a fresh crew began pre-flight checks on the same Wellington. Pilot officer Robert Chen and his crew had been briefed for that night's attack on Kiel's naval yards. The aircraft's history was mentioned only as recently repaired. No one stated that those repairs had been completed 3 hours earlier or that the bomber had absorbed over 200 hits the night before. Chen noticed the pale fabric patches immediately, dozens of squares visible along fuselage and wings. A few holes still gaped in the tail, their edges whispering in the breeze. He walked a full circuit of the aircraft, running a hand over patch after patch, then glanced at Fricks with a questioning look. The crew chief kept his explanation short. She took a beating last night. Every structural member's been checked or replaced. She's fully airworthy. Delivered in the steady tone of a man who had been servicing Wellingtons since before the war, it was enough for Chen. He trusted the type. If anything, the patches reassured him, proof the aircraft had survived what should have destroyed it. In many ways, our Robert was now the most thoroughly inspected Wellington on the station. The crew boarded at 20:30 hours. Engine startup, taxiing, and control checks revealed no unusual behavior. The new compass performed flawlessly. Control surfaces responded sharply. As Chen opened the throttles and felt the Wellington gather speed, he sensed the same dependable weight he'd felt on every mission before. At 20:37, our Robert lifted cleanly into the darkening sky and turned toward the North Sea. The wireless operator confirmed his equipment was functioning perfectly. The rewired harness gave no trouble. In the rear turret, the gunner swept through his full arc, satisfied that hydraulic repairs were sound. To anyone familiar with Bomber Command's relentless operational demands, the significance was obvious. Aircraft could not sit idle. Every grounded bomber meant fewer attacking Germany that night. The ability to restore a nearly wrecked Wellington to service in under a day was more than impressive. It directly strengthened Britain's ability to continue the offensive. Wallace's claim that geodetic aircraft could be repaired rapidly and locally, without depot facilities, had been proven beyond doubt. By 2200 hours, Chen crossed the Danish coastline. The patched fabric held firm, the framework carried loads without complaint. Somewhere below, German night fighters were climbing to intercept, their pilots convinced that fabric-skinned bombers would break apart under focused fire, an assumption the Wellington had repeatedly disproved. Fricks's incident report, filed on April 7, 1941, spread through Bomber Command with unusual speed. Air Marshal Arthur Harris personally requested photographs, deflection data, and structural notes. What made this case remarkable wasn't simply that the aircraft survived, but that it returned to operational service almost immediately. Technical schools soon used the report as a teaching example when explaining geodetic principles to students still convinced that stressed skin metal structures represented the inevitable future. By mid-1941, enough comparable incidents existed for a formal study comparing Wellington survival rates with those of other twin-engine bombers. The results were striking. Wellingtons attacked by fighters made it home 63% of the time, versus 41% for Whitley's and 37% for Hampton's. When examining only heavily damaged aircraft, the Wellington's advantage increased dramatically. This was not anecdote, it was quantifiable proof that distributed load paths and structural redundancy saved aircraft and crews. German intelligence eventually corrected its assessments. Late 1941 Luftwaffe technical notes acknowledged the unexpected resilience of Wellington geodetic construction and instructed night fighter crews to concentrate fire on engines and cockpit rather than the fuselage. Advice that came too late for many who had underestimated the stringbag bomber. The Wellington's influence outlasted the design itself. While no major post-war aircraft adopted full geodetic construction, it was far too labor-intensive. Its underlying principles shaped modern survivability philosophy. The idea that damage must not be allowed to cascade into catastrophic failure became standard. Decades later, aircraft like the A-10 Thunderbolt II embodied these lessons through redundant systems, separated engines, and structures tolerant of extensive non-critical damage, echoes of Wallace's latticework without directly repeating it. Barnes-Wallis was knighted in 1968 primarily for the bouncing bomb, yet the geodetic Wellington arguably saved far more lives. Over 11,000 served during the war, and statistical analysis suggests its structural resilience prevented roughly 2,300 additional losses. meaning more than 13,000 aircrew survived missions that might otherwise have ended in scattered debris over Europe. That patched Wellington at Mildenhall on April 6 symbolized far more than one aircraft's survival. It represented the triumph of a design philosophy that embraced distributed strength over rigid dependence, subtle geometry over brute force, and a quiet, mathematical elegance that kept aircraft intact when logic said they should fall from the sky.